Okay, we were talking about association. We'd looked at scatterplots, started to look at scatterplots last time, and we're introducing the idea of association. And I put this scatterplot up that has two sets of parallel lines here. These horizontal ones are at the vertical mean plus or minus 1 standard deviation, I believe, of the vertical variable, and the horizontal lines are, the vertical lines are at the horizontal mean plus or minus 1 standard deviation of the variable that's plotted on the x-axis. So this again is the point of averages. The coordinates of that red square are the average of x and the average of y. All right, so a few things to do here. One is to give you to talk about something that will confuse some of you when you see it in the homework. So this is a hint. Suppose that these lines had been drawn at plus or minus at the means plus or minus 2 standard deviation, mean plus or minus 2 standard deviation. Let's think about how many of the points would be in that square, in that box. It's a rectangle. It's not a square. So Chebyshev's inequality would tell us that the fraction of values of x that are in between the two parallel lines that are at the mean plus or minus 2 standard deviations is what? What would Chebyshev's inequality say? It would say that that value is at least something or at most something, first of all. At least. Okay, so what's within the range is at least some fraction of the data. And if we're looking at the mean plus or minus 2 standard deviations, what fraction would need to be in that range? Two-thirds. We have a vote for two-thirds. Sorry? We can say two-thirds is true, but we can say more than that. It's actually some number that's even bigger than two-thirds. 75%. I like 75% better. Okay. The amount that would be beyond 2 standard deviations away from the mean is at most 1 divided by 2 squared, right? 1/4. So the amount that's outside is at most 25%. The amount that's inside is at least 75%. Okay? Now let's suppose that we had this box was the mean plus or minus 2 standard deviations in this direction. What fraction of the y values would need to be between those limits? Again, the fraction that would be beyond 2 standard deviations is at most 1/4. 1/2 squared. The fraction that's within is at least 3/4. Right? So if the fraction that of x values that are in this range is at least 3/4 of the x values, and the fraction of y values that are in this range is at least 3/4 of the y values, what fraction of numbers must be in the box, in the whole rectangle? Sorry? There is a homework problem not unlike that. Sorry? 9 over 60? 16? 9 over 16? So you're going 3/4 squared? Is that what? So 75% of 75%? Okay, there's one vote. Anybody want to get behind that or propose something else? Or all right, so if these lines had been drawn at plus or minus 2 standard deviations, plus or minus 2 standard deviations away from the mean, then we lose at most 25%. We lose at most 25%. How much is left in the middle? So the claim that what's left in the middle is 3/4 of 3/4 is kind of saying when we throw out that stuff, we lose at most 25%. And when we throw out this stuff, we lose at most 25% of what's left. Right? Yes? 1 minus 0.25 squared. Okay. That would be an even bigger number than 0.75, right? So let's just, the proposal is maybe the answer is 1 minus a quarter squared. So let's think, if we lose, if after we throw out that, what's left is at least 75%, but not necessarily 80, not necessarily 90. When we throw out this, we've got to be throwing out something more. So the answer when we throw out this needs to be somehow less than 75%. But if 1 minus 0.25 squared is bigger than 75%. So you're sort of saying that you're throwing out less. So that doesn't pass a sniff test, as it were, right? It's sort of, the number ought to be less than 75%. The question is how much. Does that make sense to everybody? Okay, so the claim that what's left is at least 75% of 75%, right, at least 0.75 squared, is saying that when you throw out this, you lose 25. When you throw out that, you lose at most 25% of what's left. Okay? Does Chebyshev's inequality sit? For that to be true, what will we need to be applying Chebyshev's inequality to? Right? We start off with the standard deviation of all the y values. And if we want to say that when we throw out what's beyond 2 standard deviations of all the y values, we lose at most 25% of what's left. The argument is a little bit more subtle, right? It would be true if we were looking at the standard deviation of the y values that are left after you throw out the points that have extreme x values, right? Throw out some points, look at what's left, take the standard deviation of the y values of what's left. If you then threw away what was beyond 2 standard deviations of those remaining things, you'd be throwing away at most a quarter of those remaining things. Okay? But that's not what the story is. We're using the standard deviation of all the y values, not the standard deviation of the y values that are left after you throw away those x's. Okay? So all you know is you lose at most 25%, you lose at most 25% of the whole each time. So all you really know is that what's left is at least 1 minus 25% minus 25%. What's left is at least 50%. Okay? In order to say that what's left is 75% of 75%, you would need to know that when you throw away the extremes, you're only throwing away 25% of what's left, not 25% of the whole. That would be true if the standard deviation of what was left of the points, if you throw away the values of x that are out there, and now you just look at these points that are in the middle, you take the standard deviation of their y values. And now you exclude everything that is more than 2 standard deviations of those, right? Not of the whole, but just of those. Then it would be 75% of 75%. Does that make sense? Yeah. Okay. That's a homework hit. All right. So the mean of x and the mean of y gives us the point of averages. And then we've got that plus or minus, these bars are at 1 standard deviation. And those are 4 numbers that tell us something about these 2 variables. But from those 4 numbers, the 2 standard deviations and the 2 means, we really don't know what shape the scatter plot has. It doesn't tell us a lot about the shape. It doesn't tell us much. It doesn't tell us anything about the relationship between these 2 variables. Now, what we do see when we look at the scatter plot is vaguely football shaped. It's a little heteroscedastic. There's more scatter down here than there is up here, than there is over there. And typically, if you looked at a little slice over here for a large value of the verbal GMAT, the average value, the quantitative GMAT in that little slice would be above average for the whole group. And typically, if it took a little slice below the average value of the verbal, the average value of the quantitative in that slice would be a little bit below the average value for the group as a whole. So that's sort of positive association. On the whole, the values of one variable tend to be bigger when the value of the other variable is bigger, right? And on the whole, value of one tends to be smaller when the other is smaller. So that's positive association, and that's somehow missing from the 4 numbers. We don't get the overall picture from just those 4 numbers. So what we're going to talk about is, introducing another number to help summarize the plot, which is the correlation coefficient. We're going to talk about that in some depth over the next couple of chapters. But the idea of association is simply from knowing the value of one of the variables, can you deduce anything about the value of the other? Does it somehow give you any information about the value of the other? And here it does. If I know that the value of the verbal GMAT is bigger than average, then in most cases, the value of the quantitative GMAT is going to be above average, right? Or at least the typical value of the quantitative GMAT for higher than average values of GMAT is going to be higher than average, and similarly for below average. Does that make sense? So one is telling you a little bit about the other. That's association. This association is pretty weak. It doesn't give you a lot of information because there's a whole lot of scatter still in every vertical strip. The scatter in the vertical strips is comparable to the overall scatter in the whole plot. Okay, if this were a nice tight little band like that, then compared to the overall vertical scatter, the scatter in a little vertical strip would be small. We'd have much stronger association. Knowing the value of one variable would tell you a lot more about the value of the other. Okay, this tool may well be confusing. If it helps, it helps. If it doesn't, don't worry about it. What this is doing is superposing two different histograms. The blue histogram is the histogram of verbal GMAT for all 913 students in this data set. This is the data set we've been looking at before. It's the verbal and quantitative GMAT scores, undergrad and first year MBA GPAs for these 913 students. Okay, so the blue histogram is the histogram of the verbal GMAT scores, and the green histogram that's superposed on it is a histogram of the verbal GMAT scores of not everybody, but a subset. So what's the subset? In this case, it's the subset of students who had a quantitative GMAT score bigger than 30. Okay? So let's make this. Let's look back at this plot for a second here. All right. Again, this is a plot of quantitative versus verbal GMAT. And the quantitative GMAT score, the average quantitative GMAT score, reading off, I put the cursor over the dot, and the average, the value of the quantitative is about 34.5. Okay? Now, the claim that these things are positively associated is sort of saying if I looked at the average value of the quantitative GMAT score for students whose verbal GMAT score was here above average, then the average quantitative GMAT score for those students should be higher than the overall average. Right? Okay, so let's see if we can make this histogram tool do that. So we want to look at quantitative GMAT scores, and we want to look at them for students whose verbal GMAT score. We're going to compare everybody to those whose verbal GMAT score is somewhat above average. Let's make it be, say, the range 38 to 42. I'm not doing this for any particular reason, but I'm not picking those numbers for any particular reason other than that they're above average. Okay, so what do we see? The blue is everybody. The green is, so the verbal, try again. The blue histogram is a histogram of the quantitative GMAT score for all 913 students. Okay? The green histogram is a histogram of the quantitative GMAT score for the 232 students whose verbal GMAT score was between 38 and 42. Okay, so we've taken a slice through the data, and we're looking at how the distribution of those students' quantitative GMAT score compares to the overall distribution of quantitative GMAT scores for everybody. All right, so what do we see? Well, first of all, if you look at the mean for everybody, it's 35. If you look at the mean for the subset, it's bigger, right? That's a sign of positive association. We're taking a slice through at a value that's above the mean, and it turns out that the other variable is then above its mean, right? Okay. If you look at what's going on, there are more very high values for the subset than there are, proportionally more very high values for the subset than there are for the group as a whole, right? These people, the people who are in this bin, are also on the blue bin. right? It's just that the bin heights are changing. They're normalized to have area 100% because they're histograms, right? So a bin of this height in green is fewer students than a bin of the same height in blue. Because what's being represented by the area of this bin is the fraction of students in this subset. What's the area of the blue bin is the fraction of students overall. Okay. All right, what else is going on? The whole distribution is kind of shifted up a little bit. We have these the bins corresponding to higher values have a relatively higher percentage of students in the subset than they do students overall. Again, it's sort of showing that typically you get larger values of the quantitative GMAT score when students have higher values of the verbal GMAT score. Okay, so does this? It's a way of like quantifying that slice through a scatter plot idea. We're taking a slice of the scatter plot that picks out those students whose verbal GMAT scores are between 38 and 42, and it's looking at the distribution of their quantitative GMAT compared to everybody's. All right, let's look at a couple of others. Okay, so what are we seeing now? Does somebody want to explain it to me? Okay, it's a histogram of what? What variable are we seeing a histogram of?
First year MBA GPA.
Okay, first year MBA GPA, that's what this menu here is telling us. And now we've got the blue is everybody, all 913 students, and the green is a subset. Who are the green students? Who are the students represented in green here? Okay. All right. So it's the 46 students whose undergraduate GPA was between 2 and 2.5. Okay. And what do we see? Well, the average value of the first year MBA GPA for those 46 students is a little lower than it is overall for the whole group. Not surprising. It's not that much lower, right? Okay. So again, this sort of the association is not that strong. If you look at the histograms, right, again, the whole group now is kind of off to the right a little bit from where the subset is. Right? So the subset is a little below average. Their distribution is shifted downwards a little bit. It's not quite the same shape either, but low values are more common among the students in the subset compared to the students as a whole. Right? So that's still showing positive association because below average values of one tend to occur with below average values of the other variable. Make sense? Questions? The convention here is whatever bin is shorter gets plotted in front, right? So if you see a bin like this, the blue, if it's over here at all, is down so low that you can't even see it, right? It's not hidden behind. Right? Okay. What properties does this scatter plot have? Parabola. Okay, yeah, it's not a line, right? Okay, so the scatter plot shows nonlinear association. Yes. Okay. Does this scatter plot look homoscedastic or heteroscedastic? Yeah, I think it's pretty close to homoscedastic. Whoops. So that's why I should click a different one then, huh? Okay, and what about the association? Does knowing the value of x tell you very much about the value of y?
No.
Well, compare the scatter take a little vertical strip, right? You take a little vertical strip like this and look at the vertical scatter in that little strip. compared to the overall vertical scatter of the plot. Right? It's a relatively small fraction. So I would say that this is tending towards stronger association. And now we get to see whether I'm consistent with how I programmed this, which is always the moment of truth. I hold my breath. What did I get? Who knows what I got? Try again. What's going on there?
See the answer.
See the answer. Huh. Now I get to see the this is again I think this issue of resizing things. B and C and F. Okay, well, so I guess, good guess. Yeah, okay, let's reload the page again and get a different example. Yes?
Is there ever a time where you'll have a homoscedastic plot that is not a strong correlation?
Sure. Yeah. So the question was, that's why it didn't light up. We've got, hang on. High security. All right. So the question was, can you ever have homoscedastic and not strong association? And this is almost homoscedastic and pretty weak association. But basically, if you had a scatter plot that looked like this, that's sort of homoscedastic and really, really weak association. That you look at the scatter in any little slice, and the scatter in that slice is about the same as the overall scatter in the plot. Knowing the value of x isn't telling you much about the value of y.
Okay, so the strong correlation is the ratio, not just how
It's the ratio, yeah. So basically, what we're looking at, strong association is scatter typically in a vertical slice is much smaller than the overall vertical scatter in the plot. Let's see what we got here. Okay, here's a fun one. What do we see? Okay. Up, flat, up. Okay. This is, if you tried to draw a line through this, if you tried to match this with a line, you'd be below all those points. If you tried to match this with a line, you'd be above all those points. You try to match the middle, you miss the ends systematically. Right? So you have systematic differences from a line. It's nonlinearly associated, nonlinear pattern. What else?
I have a quick question.
Yes.
So to be linear, it has to go through the whole graph, right?
Well, linear association would be if you try to do your best job of running a line through it, then points are scattered around the line without kind of systematically being only above the line in some places and only below in others, or almost all above in some places and almost all below in others. If you get a systematic departure from a line like this, most of the points would be above here, then that's nonlinearity. So, so basically, linear scatter plots look football shaped, give or take heteroscedasticity or something like that. Okay, heteroscedastic or homoscedastic?
Hetero.
Hetero. Okay, a lot more scatter, vertical scatter in this region than in this region, for the sake of argument. Okay, association weak or strong? Judgment call, to some extent. I mean, for a big chunk of the plot, knowing the value of x doesn't tell you much about y at all. Right? And overall, the vertical scatter, I mean, here, there are some ranges of x where knowing x tells you a lot about y. But kind of overall, it's not very informative. So I'm going to say nonlinear, heteroscedastic, and weak association. Okay, and I'm going to be consistent with what I thought when I coded it up. So lucky me. Let's do another one. Okay, not that different from the last. What are the salient differences between this and the last example?
This one has better association.
Much stronger association, yes? And it's homoscedastic, right? The scatter in any little vertical strip is about the same. It's probably a little bit more severely nonlinear, so we're going to go nonlinear, homoscedastic, and strong association. Right? So these are qualitative things. I'm trying to make the examples fairly clear so that when you come to do it in the homework, if you saw like 1 point over here, that doesn't mean it's all of a sudden heteroscedastic, right? Okay, should be fairly pronounced. Okay, questions about that stuff? Back when we were talking about reasoning and fallacies, we mentioned the post hoc fallacy, post hoc ergo propter hoc. That fallacy, cum hoc ergo propter hoc and post hoc ergo propter hoc, get committed a lot. Sorry. In the context of conflating association and causation. So cum hoc ergo propter hoc is two things happen together, therefore one causes the other. Post hoc ergo propter hoc, one thing follows another, therefore one caused the other. What was I said? First thing is they happen together, therefore one causes the other. The second is one follows the other, therefore one causes the other. So here's an example that was at the beginning of the chapter. It turns out if you look at the association between how much people spend on healthcare in, say, a 6-month period and how long they live, those people who spend the most tend to live the shortest time, right? So a causal argument would be that healthcare is bad for you. You spend a lot on healthcare. It causes you to die very shortly afterwards, right? Okay. But what we actually think happens is that when people are really, really, really sick, they spend a lot on healthcare and they die anyway, right? It's sort of they might have taken them even longer to die had they not had the healthcare. Yes, you can't tell from that situation which way the causal arrow goes if it goes any way at all. In this case, there's sort of a third thing, which is people's health, which is influencing both their life expectancy and their healthcare costs. Yes, in the U.S. Here's an example. So across countries, there's a strong positive association between per capita dietary sugar intake and various forms of cancer. Therefore, sugar probably causes cancer. Right. There's a couple of issues with this argument. One of them has to do with the fact that we're looking at countries rather than looking at individuals, but let's skip that issue. That's an ecological correlation question, which we'll come to in the next chapter. But what about this argument? What else? I mean, is that evidence that sugar causes cancer? I mean, there's an association. Okay, there could be confounding factors, right? Confounding is a term of art. There could be something else that produces both the higher sugar intake and the increased cancer incidence, or at least cancer diagnosis. Right? What are some things that we kind of believe influence the incidence of cancer diagnoses? Doctors? Having more doctors? Okay, so to some extent, better health care, better chances are you get diagnosed with something if you have it. Okay, first world countries, more likely to get certain diagnoses than third world countries, whether you have the disease or not. Okay. Cancer, by and large, is a disease of old age. You live long enough, you're going to get some kind of cancer. Not necessarily one you'll die of, but okay. So if you're in a country with a long life expectancy, then you will likely live long enough to get some kind of cancer. Okay? Just saying, yeah. Okay, so, and where's sugar intake high? Wealthier countries. Okay, sugar and fat are expensive on a global scale. Yes?
Well, that says dietary sugar. Is that referring to like Splenda or something like that?
No. In your diet, things you eat. Yeah, dietary sugar intake, meaning sugar you eat rather than sugar you wear on your body or something. Sugar in your food, sugar in your diet. Okay, so sugar, especially refined sugar, is relatively expensive on a global scale. So is fat. So is protein, right? Carbs are the relatively cheap thing. So sugar intake is associated with wealth. So is longevity. So is medical care. So is a lot of other things that go along with that. What else might be associated with wealth that could explain this association? So there's sort of the hidden variable here, or a hidden variable here is wealth, affluence of the country. Yes? It can be affecting both directly and indirectly. Right. So some people think stress leads to cancer. Okay, I don't have an opinion, but if you think that the stress of sitting in traffic is bigger than the stress of wondering whether next year's crop is going to come in, then maybe stress is associated with wealth as well. Yep, sorry.
Some people think that cell phone use increases the risk of cancer. That would be a little.
Okay, so if cell phone use causes cancer, and I think the evidence for that right now is pretty weak, but doesn't mean it isn't true, then more affluent countries have more cell phones per capita, and that might be causing a higher incidence in cancer as well. Yes?
Are we talking about any kind of cancer? Like, what about like exposure to the sun?
Exposure to the sun. Okay, so skin cancers, it's hard to tell which way it would cut. The question is who spends more time outdoors at peak solar times. I think a lot of the more affluent countries are actually less equatorial, and so it might be, and also less agrarian. So it might be that would cut the other way. I'm not sure. Yes. Obesity. If obesity leads to cancer, people believe it leads to heart disease and cardiovascular disease in general. But if it's linked to cancer, then okay. Some people believe that fat intake causes cancer, especially animal fat. Well, the countries that can afford sugar are the countries that can afford fat, to a large extent. Yes.
Cigarette smoking as well.
Cigarette smoking. Okay, there again, there's a certain level of affluence that's maybe necessary to afford cigarettes. I don't actually know what the statistics are like across countries. I think that in more developed countries, cigarette smoking is decreasing compared to what it is in some less affluent countries at least. But clearly, if you're in extreme poverty, you don't get it. Yeah. Other ideas? Right. So association. If there isn't an intervention, right? If we didn't basically take some group of people experimentally and insist that some of them eat more sugar than the others, to pick a subset of them at random, give some of them more sugar, some of them less sugar, follow them for a number of years, and look at what happens to the incidence of cancer among those people who were sort of nominally the same but only randomly assigned one treatment or another, then it's very difficult to attribute differences in the outcome to differences in the sugar intake, because a whole lot of other things go with that. Right? That's not the only factor that differs for these groups. There are a lot of other factors that differ from these groups, across these groups. Okay. Given that we're here in the Earth Science Building, maybe we should talk about the last example. Something that I do some research on is earthquake prediction. And there are people who claim to be able to predict earthquakes based on all kinds of phenomena, ranging from how long back in the days when we had newspapers and read classified ads in newspapers, people had lost pet ads in the newspapers. And some scientists have looked at things like how long are the lost pet ad columns, like how many pets went missing, just before earthquakes. Right, as sort of evidence that animal behavior predicts earthquakes, and they sort of look at associations between the length of the lost pet ad columns and earthquake incidence, earthquake occurrence. Some people have looked at things like the web building behavior of spiders, or the activity of cockroaches, which they put in some box where they measure the electrical activity associated with them walking on some touch plate. Okay, I mean, there's some really wild things that people have looked at to try to predict earthquakes. Well, people are looking at things like the chemical composition and temperature of groundwater in wells. They're looking at radon gas. They're looking at the movement of the ground, certainly. They're looking at electrical signals in the ground, electromagnetic waves, looking at the resistance of the ground across faults. All, some of these have physical theories behind them. Some of them are just utterly empirical. But if you look at the predictions that have claimed success, one of the biggest groups doing this is a group in Greece, and they're using electrical signals. And if you actually look at what they're doing, you look at how successful they are, they tend to be more successful if you run the time axis backwards than if you run the time axis forwards. Okay, so what you find is when they issue a prediction, it's pretty likely that there was an earthquake a little while before the prediction. It's a little less likely that there's an earthquake a little while after the prediction. So what's happening, right? Well, everybody in California knows that earthquakes have aftershocks, right? And so if you were going to guess when an earthquake is going to happen, a pretty good guess would be right after another earthquake. Okay. A very good algorithm for predicting the weather is, what's tomorrow's weather going to be like? It's going to be like today. Right? So the sort of first order weather prediction is predict that tomorrow is going to be like today. You'll be wrong some fraction of the time. There are places where that's phenomenally accurate. Right? There's places where that actually works better than the official predictions do. I had a student study this in a graduate course not that long ago. Okay, so to first order, predicting earthquakes the same way will do a pretty good job. If there was an earthquake yesterday, predict that there's going to be one today. If there wasn't one yesterday, predict that there won't be. It actually works pretty well, but it's not really giving you a whole lot of extra information, right? You sort of, okay, so if you wanted to evaluate how effective earthquake predictions are, you'd probably want to compare them not to sort of no prediction at all, but to a really naive prediction that does something like that. If there was an earthquake yesterday, predict that there will be one today. Okay, because that's exploiting the clustering of earthquakes to tell you something. All right. Blah, blah, blah.
I had a quick question about predictions.
Please.
Since you've been doing a lot of research on this, have you ever come across Webbot?
Webbot?
Yeah. It's supposed to be like this supercomputer, like it's been programmed to predict a lot of things. I don't know if you came across
No, the only thing I know of is a Webbot is like something that scours the web for news or something like that. So I haven't heard of Webbot as a computer of stuff, but I'll look for it. Okay. Is it time to take a little break? You guys stretch your legs. All right. Am I live now? All right. Okay, so here is a scatter plot of the GMAT data again. We have a new little number down here on the bottom in an invisible font that says R.35. So that number R is the correlation coefficient. It is a measure of the strength of linear association. So it doesn't measure all kinds of association. It measures linear association. What is linear association? Well, linear association is, it's like how well do the points follow a straight line? But we can have points where the association is really, a scatter plot where the association is really, really strong, but a nonlinear pattern. We can have a nonlinear pattern, very strong association, but weak linear association because no line does a very good job of predicting the points. No line goes to the points very well. So we'll get to more detail momentarily, but 0.35 is a moderate number. The correlation coefficient is always between -1 and +1. Can't be bigger than 1 or smaller than -1. R equals 0 means no linear association. In this case, we have the association here is, what association there is pretty linear, right? It's just roughly football shaped. There's some heteroscedasticity, but basically 0.35 is saying, well, yeah, you can learn a little bit. If you're above average in one, you're going to tend to be above average in the other, but it's not that strong an effect. The scatter in a vertical strip is pretty comparable to the overall scatter in the plot. So let's look at how the correlation coefficient varies as we change the number of points in a scatter plot, how the visual appearance of the scatter plot changes as we change the number of points in the correlation coefficient. So this is an example of a correlation coefficient of 0, n equals 50 points. It's scattered. There's no trend to what's going on. If there's linear association, there's going to be a general trend. You could sort of fit a line that will follow the points somewhat. It will account for some of the variability. All right, what happens as R gets bigger? Okay, 0.3. Now we're starting to see a little bit of a positive trend to what's going on. Yes, not very strong, still a lot of scatter. Okay, 0.4, getting a little bit more tightly clustered. 0.5, 0.6. As it grows, the points get more tightly scattered until eventually, if they all fall exactly on a straight line, the correlation coefficient is +1 if the line slopes up. It's -1 if the line slopes down. So as we go down, so there's correlation coefficient of -1. All the points fall on a line that slopes down. And as we increase the correlation coefficient from -1, we get more and more and more scatter. Generally a negative trend as long as R is negative. By the time we get to roughly 0, there's no trend up or down in the data, but the data are quite scattered around essentially a horizontal line. And then again, as the correlation coefficient climbs, they get more and more tightly clustered around a line that has positive slope instead of negative slope. Right? So the number of points increases. You get a different visual appearance that's coming just from the fact that there's more points, right? It's somehow, things look a little denser in the middle, not because 0.66 is a huge correlation coefficient, but just because there's a lot more points. Now, okay, so there's 200 points, correlation coefficient of 0.6, 0.7. Again, if I make this -1, they're going to all lie on a straight line with negative slope, +1, straight line with positive slope. All right, so let's start playing the guessing game. All right, there are 50 points in this scatter plot. Let me make this just slightly smaller, if I can. All right, I can't quite. That work. All right, 50 points. What would you guess the correlation coefficient to be? Okay, bigger than 0, less than 0. Less than 0. Okay. Generally, there's a downward trend. It's very weak. Yes?
Like
So minus point,
2.
0.2, 0.5, 0.1, 0.4. I'm gonna give us a minus 0.1, and let's. Well, okay, let's look at what the range was to see. That's giving me a better idea. So it's actually minus 0.2 was a better guess, because that's the center of that range, and that's what it's coming from. So whoever guessed minus 0.2 is doing better than I am. All right, let's. Where's reload? Yes, I'm sure. Okay, negative again. Yep. Maybe a little stronger.
4, 5.
Okay. All right, so you get the idea. Play with this. When there are more points, you get a different visual appearance for the same correlation coefficient, right? So you need to kind of train your brain and your eyes to work together to judge this to some extent. Okay. All right. These data follow a lovely pattern, right? A parabola. Yes? But the correlation coefficient is 0. They follow a nice pattern, but that pattern is not linear at all. If I did my best job of fitting a line to these data, it would be a horizontal line. Yes? So because the slope of that line would be 0, the correlation coefficient is 0. If the slope of the line would have been positive, correlation coefficient would have been positive. Negative, negative. So, okay. All right, so this is to drive home the idea that the correlation coefficient measures association, but it only measures linear association, not nonlinear association. So here is a slightly less clean example. Here we've got we got nonlinear association, right? This thing is all sinuous, S-shaped, whatever. The scatter in a vertical strip is relatively small compared to the overall scatter in the plot, so the association is pretty strong. The correlation coefficient is 0.7. It's not small, but why is it not small? It's not because of this clustering. It's not because of this. It's because if you fit a line to it, right, the line does a pretty good job of predicting the value. It's systematically above in some places, systematically below, but somehow a lot of the variation in the vertical variable can be, quote unquote, explained by a straight line. Straight line takes up most of the difference. Okay, is this all right?
So I mean, the line that we draw through it, does it take into account like just y values? Because from what I see, it kind of just measures like the distance from like the line. Y.
Okay, so what R is basically measuring, I mean, another way to think about it is if you put a line through this and you compare the overall scatter in the plot to how much scatter there is around the line. You sort of subtracted the line from each point. Then if that ratio is big, if after you subtract the line, there's not much scatter left compared to what you started with, then the correlation coefficient will be big. Okay. If that line slopes up, it'll be big and positive. If that line slopes down, R will be big and negative. Yes? It's not the slope of the line. If the line has positive slope, the correlation coefficient will be positive. If the line has negative slope, the correlation coefficient will be negative. But the R will be 1 if all the points lie on a line that has even a microscopically positive slope. So the magnitude of R is sort of measuring how near the points are to the line compared to how near they are to each other overall, vertically. Yes?
So for like, let's say there's a sine wave,
Yep.
the R would be 1, right? Because it's going like through a straight line.
If you really had a full cycle of a sine wave,
Like more than like
then the best fitting line is going to be horizontal. And you're going to, well, actually, no, if you did that, the best fitting line would probably tilt this way because you have a bunch of positive values here and a bunch of negative values there. So you're going to have a line that slopes down a little bit. you would get a negative correlation coefficient, but it wouldn't be -1 because they don't lie on the line. They're scattered around the line. Okay. Now, R is a good measure of association if the scatter plot has linear association and is homoscedastic. If it's heteroscedastic, I mean, here, if I just look at this, it looks like the best fitting line ought to be horizontal, right? There's sort of no real trend here. But because of the heteroscedasticity, this one point up there is having a pretty strong influence on the line that I would fit if I fit it by least squares, which we're going to get to pretty soon. And as a result, the correlation coefficient is, pretty different from 0, even though, this is not very strong association, right, visually. Does that make sense? Okay, so if you have heteroscedasticity, the correlation coefficient is not a very good measure of association. If you have nonlinearity, the correlation coefficient is not a very good measure of association. If you have outliers, the correlation coefficient is not a very good measure of association. So here, for most of the points, knowing the value 1 isn't telling you much at all. But because there's that one point way over there, that has huge influence on the correlation coefficient. If you fit a line to this, the line would have, positive slope. It would do a very good job of predicting the value of that point compared to a horizontal line. And as a result, the correlation coefficient ends up being big. But an outlier can also kill the correlation. So here, if you ignore this point, these points come very, very close to lying on a straight line. But I throw in this one outlier, and it knocks R down to 0.08. Okay? It just has a very large influence on the correlation coefficient. So if you have nonlinearity, heteroscedasticity, or outliers, the correlation coefficient is not a very good summary of the association. Now this is a little tool to just kind of play around and see. By clicking, you can add a point and see what its influence on R is. Now suppose I want to make R big and positive. Where should I add points? Okay, I can add points up here, or I can add points down here, right? They're both going to increase the value of the correlation coefficient. Because I'm saying that I'm making above average values of one variable associated with above average values of the other, below average with below. So that's increasing the strength of the association. Yes? Question? Right. All right. So if I want to make the correlation coefficient large and negative, then I do the opposite, right? Okay. All right. So if we have a football-shaped scatter plot, that is, the association is linear, the plot shows a homoscedastic relationship, and there are no outliers, then you can summarize that plot pretty well by 5 numbers. The average value of x, the average value of y, the standard deviation of x, the standard deviation of y, and the correlation coefficient. So from knowing that it's football-shaped, you sort of know that it's some kind of an ellipse. From knowing the SD of x and the SD of y, you can kind of figure out what the aspect ratio of the ellipse is. And from knowing the correlation coefficient, in addition, you can kind of figure out how tilted it is. All right. So far, this has all been just heuristic. We've seen, the closer the points fall to a straight line, the closer the points are to falling on a straight line, the larger the correlation coefficient is. If that straight line has a positive slope, the correlation coefficient will be positive. If the straight line has a negative slope, the correlation coefficient will be negative. Now let's talk about numerically how to compute the correlation coefficient. So it's a number that's been on this plot. Where does it come from? Right. First step in computing the correlation coefficient is to turn the list, the two lists of numbers. Remember, we're computing the correlation coefficient between 2 variables, and we need to turn each of those variables into standard units. So what is a value in standard units? Well, you take the original value, you subtract the mean of those values, and divide by the standard deviation of those values. Okay, so we take a value of verbal GMAT score, subtract the mean of the verbal GMAT scores, divide by the standard deviation of the verbal GMAT scores. Okay, we're talking about the mean and standard deviation of the same variable, right? Okay, when you So that's an affine transformation. When we talked about affine transformations, is it just the last lecture? No, that's of the form a constant times something plus a constant. Okay, so what is this? This is taking, reminder, office hours in Student Learning Center today. Okay, if I take value minus the mean divided by the standard deviation, I can write that as a constant times the value plus a constant, right? So what's the constant times the value? So that's the same as 1 over SD times the value minus the mean over the SD, right? So the multiplicative constant is this, and the additive constant is minus that, right? So this is an affine transformation. Okay, and you can go back and forth. If you have the value in standard units times the SD plus the mean takes you back to the original units of measurement. All right. If you have a value that is above the mean, then when you convert it to standard units, it's going to be positive. If you have a value that's below the mean, when you convert it to standard units, it's going to be negative. All right, so let's, the correlation coefficient is easy to calculate once you have the notion of converting things to standard units. What you do to find the correlation coefficient between x and y is you convert x to standard units, you convert y to standard units, and you take the average value of their product. Okay, you need to keep the pairing right. We're talking about, if we're looking at verbal GMAT and quantitative GMAT, the value of verbal GMAT in standard units that we multiply times a given value of quantitative GMAT in standard units has to be for the same student, right? We got to keep the pairing, right? We're multiplying two measurements for the same individuals. Got to keep the order the same. Right, so here's an example. We have a list of weights of people in pounds and their heights in inches. So this is one person who was 71 inches tall and weighed 216 pounds. Here's a scatter plot for these fake data. Oops. Starts down here. What would you guess the correlation coefficient to be? There are not very many points there, but 0.6, 0.7, somewhere around there. Yeah. Positive, clearly positive. Yeah. All right. Okay, so the point of averages is 64.4 inches, 182.5 pounds. The SD of the heights is 7.17 inches. The SD of the weights is 49.06 pounds. So how do we calculate the correlation coefficient? We have these two lists, 71, 72, 61, et cetera, are the heights. 216, 264, 186, et cetera, are the weights. So now we've got the heights here, the weights here for the same individual. So the 71 inches is the same person who weighed 216 pounds. Okay, we're keeping individuals together. We need to convert the height into standard units. Well, how did we get 0.921 from 71? Right. We took 71, subtracted the mean, which is 64.4, and divided by the standard deviation, which is 7.17. Okay, so that's 0.921. To convert 216 to standard units, we take 216, subtract 182.5, that's the mean of the weights, and then divide by the standard deviation of the weights, which was 49.06 pounds. So if we do that, we get 0.683. Now, just as a sanity check, 71 is above 64.4. It's above average. So this ought to be a positive value, which it is. Similarly, 216 is above average. It's above 182.5. So this ought to be a positive value, which it is. Now what we do is we take this value of standard units times that value in standard units, get the product. We do that for all the measurements. We now average these products. Okay, we add up these numbers and divide by how many there are. Are there 10 of them? Yes. Good. All right. So 0.9 correlation coefficient, according to this. So that's rather bigger than I would have guessed from looking at the data. Okay, so yep, yes.
I mean, could that be because like the lack of points is kind of hard to predict?
I think that probably it's this point way down here is having a pretty strong influence on the correlation coefficient. Yeah. We can try reloading the page. Yes. Send my personal information all over the web. There. At least back to my server. Okay, there's a point over here. Right, there's points down there. This definitely looks weaker. Right? At any rate, the same kind of calculation going on. In this case, the correlation coefficient is a little under a half. Okay. So practice. Reload the page, get some practice. All right. Now, when you convert a list, yes, question. We're calculating, well, in this example, sort of what's originally given are the values in original units. And then in order to convert to SU, what we would do is we'd find the mean of this list, the standard deviation of this list. To convert 199 to standard units, we would take 199 minus the mean of the list divided by the standard deviation of the list. And so the mean of the list is, in this case, being told to you that the mean of the weights is 195.1 and the standard deviation of the weights is 45.99. So if we take 199, subtract 195.1, divide by 45.99, we get 0.085. All right. Let's think about what goes on in this calculation. So first thing that goes on is we convert each of the lists to standard units. If I add the same number, suppose that my yardstick is 2 inches too short. Okay, so every height measurement is off by 2 inches. Is that going to change the value of the correlation coefficient if I made that kind of measurement error? No. Okay, because all that's going to do, it's going to shift every value by 2 inches. It's going to shift the mean by 2 inches as well. And when I convert to standard units, I'm subtracting the mean. So I'm subtracting off exactly that difference. It's going to just cancel out. Okay. If I measured people's height in centimeters instead of measuring their height in inches, would that change the value of the correlation coefficient? Okay. The relationship between them is that a centimeter is 2.54 inches. Sorry, other way around. An inch is 2.54 centimeters, right? So I'd be multiplying every measurement by 2.54. When I convert to standard units, what's going to happen to the standard deviation? Standard deviation is going to be bigger by a factor of 2.54. So when I divide by that, it's just going to cancel that factor of 2.54, and I'm going to get exactly the same values in standard units. So converting to standard units, because it subtracts the mean, because it divides by the standard deviation, any affine transformation I make to one variable is going to go away. Okay? So one of the reasons for going to standard units, what it means to be standard, is that it somehow removed any affine transformation. It's putting things on a scale where after you transform things to standard units, anybody want to guess what the average of those numbers is? I have a guess of 0. I like that guess. Yeah, after you convert to standard units, the mean of the new list is 0. And the standard deviation of the new list is 1. Okay, so no matter what units you started with, after you do the transformation, what you get has mean 0 and standard deviation 1. Can we prove that that would be the case? Let's take just a few seconds to do some math for grins. Okay, so we've got some list of numbers, x1, x2 up onto xn. Okay? And now what we're going to do, let's let, just to be fancy, we're going to call the mean x bar is 1 over n times the sum from j equals 1 to n of xj. Okay, that's the mean. Okay? And then we've got the, and I'm just going to call, what do I want to use for this symbol? I don't really want to use S. I'll use S. Okay. S is equal to 1 over n Okay, so that's the RMS of the deviations from the mean. I take each element of the list. From it, I subtract the mean. That's the list of deviations from the mean. And then I average those deviations from the mean. I get the mean of the squares. So I square them, add them up, divide by how many there are, and then I take the square root of the result. So that's the RMS of the deviations from the mean. Okay? And now, question is, if I take this original list and I convert it to standard units by subtracting x bar from each element and dividing the result by s, what is the mean? What are the mean and the standard deviation of the result? So let's do the mean because that'll be fairly quick and painless. So I've got my new list looks like x1 minus x bar over s, x2 minus x bar over s, so forth onto xn minus x bar over s. Okay, I've got n values. And now I want to ask, what's the mean of that list? Well, 1 over n times the sum from j equals 1 to n of xj minus x bar over s, right? That's what we're trying to find. Okay, so I can pull the 1 over s out front, right? That's just a constant. So that might as well be 1 over s times that. This is a sum, right? I can break the sum into two pieces. This is like 1 over s, 1 over n times the sum j equals 1 to n xj minus the sum from j equals 1 to n x bar, right? The summand here, this thing inside, doesn't depend on n, right? I'm just adding x bar to itself n times. What happens if I add x bar to itself n times? I get n times x bar, right? Okay, so this sum is just n times x bar. So far, so good? Okay. Now, I'm going to distribute the 1 over n. I've got 1 over s times 1 over n sum j equals 1 to n xj minus 1 over n times x bar. So that's just x bar, right? This is x bar, right? That's the definition of the mean. So I don't know if you can't see this. This doesn't go up, it goes sideways. Can you guys see it? Okay, so this is 1 over s times x bar minus x bar. So it's 0. Is that all right?
Yeah.
Okay. You will not be expected to reproduce this. But the point is that if you take a list and convert it to standard units, the mean of the new list is 0. And you can take my word for it that the standard deviation of the new list is 1. Or you can work it out for yourself. Or you can look at the footnotes because it's probably buried in there somewhere as well. All right, so because the correlation coefficient in calculating it, any affine transformation of either variable cancels out. If you add the same number to either list, to every element of either list, it doesn't change the correlation coefficient. You can add 7 to one list and 2 to the other list. 7 to every element of one list, 2 to every element of the other list, doesn't change the value of the correlation coefficient. If I multiply every element of the first list by 15, that doesn't change the correlation coefficient. If I multiply the first list, every element of the first list by -3, every element of the second list by -2, I get the same value of the correlation coefficient. If I multiply the first list, every element of it by -3, and every element of the second list by 2, so one by a negative number, the other by a positive number, the correlation coefficient will have the same magnitude, but its sign will change. Its sign will flip. Okay. All right. There you go. That's what we're not going to do. Okay. Let's just do a quick fill in the blank for a couple of these to get the rhythm of the calculation and then go on. So here's an example. There's a scatter plot of some fictitious rain and temperature data. So average temperature over the year and average rainfall in inches in 10 made-up places. So it looks from this like it's a pretty weak association, maybe slightly negative, because this point is going to tend to pull a line to have negative slope. Okay. The first thing we need to do to calculate the correlation coefficient is find the mean and the standard deviation of both of these lists in order to be able to convert the list to standard units, right? Okay, so really wondering whether it's worthwhile doing arithmetic at the board or not. I've got heads shaking no, don't bother. Okay, you guys can sort this out. All right, it's arithmetic. Okay. Let's do something a little bit more conceptual, ecological correlation. All right. There's a big difference between the correlation of individuals and the correlation coefficient for measurements made on individuals and the correlation coefficient for measurements that are averages for different groups of individuals. So for instance, we looked earlier, at the very beginning of the chapter, we were looking at the correlation coefficient for verbal versus quantitative GMAT scores for the 913 students. It turned out to be 0.35. Okay. What happens if we, instead of looking at the 913 students as individuals, we take 5 averages, the average for school 1, 2, 3, 4, 5. Remember, there were 5 business schools involved. Okay. We look at the correlation coefficient for those 5 averages. It's 0.95, huge in comparison. Okay. Typically what happens when you compute a correlation coefficient for averages of groups of people instead of for the individuals is that it goes up. It doesn't have to, but that seems to happen in most cases. What's the extreme? If I divided everybody into 2 groups and calculated the average value of quantitative and verbal GMAT for one group, the average value for quantitative and verbal for the other group, there's basically 3 possibilities. The 2 averages could basically fall on a horizontal line. 2 points determine a line, right? They're going to fall on some line. If that line happens to be a horizontal line, then the correlation coefficient for those 2 averages is going to be 0. If that line happens to have positive slope, the correlation coefficient will be +1. If it happens to have negative slope, it'll be -1. Right? So ultimately, this reduction to just 2 groups, we're bound, unless we get 0, we're bound to get a big number. Okay. So what's happening is, right, the correlation coefficient is measuring how good a job a line does of predicting the data that it's computed from. Right? So if you reduce the scatter artificially by averaging the groups, so that you no longer have the within group scatter, then what's left over is likely to be better explained by a line. I mean, typically, this is not invariable, but typically, you've gotten rid of all the within group scatter, and what's left over tends to be more predictable. Okay, so the line is fitting this better. All right. So another example of this, if you think about people's ages on average, can I embarrass people by asking, like, is anybody here, so how many are freshmen? A few? Okay, any of you 16? 17? 17? So 17 is the youngest. Okay, seniors? Any seniors? Juniors? Juniors? A lot of juniors. Okay, are anybody over the age of 24? 25? Okay, so we've got a range of like 17 to something, yes, going on in the class. If you averaged people by grade and then looked at how well you could predict the average age from their grade, the difference in the average age by grade is going to be very, very close to 1 year, right? But predicting some individual's age from the individual's year is much, much harder, okay? We can find that the average age of the freshman is, 18 point something. Yes, and the average age for the sophomores is going to be 19 point something, right? But a given freshman could be quite a bit younger than 18. A given senior could be quite a bit older than 22. Yes? Okay, so there's a lot of variability. When you take the averages, that variability goes away, and what's left looks more predictable. But you need to be careful when you're interpreting correlation coefficients that are computed from averages, because people will often kind of switch subject, compute a correlation coefficient from the average, and infer something about individuals. Okay? The association between education and average level of education and average income, if you average by state, is very strong. If you look at it for individuals, it's not very strong. Okay? So grouping things by state matters. It inflates the value. Okay. Great. I'll see some of you guys at 1 o'clock.